Scientists have a problem with Polaris. From afar, the North Star's permanent position in the night sky has guided us for centuries. But from up close, it seems to behave in confusing and bizarre ways. And the closer we look, the less it makes sense. Polaris doesn't act as our stellar models predict, and it is surprisingly hard to get basic measurements for it. How can a star be so clearly visible to our eyes, but evasive to our scientific instruments? Sounds pretty ironic. So let's dive into everything we know and don't know about this enigmatic star. I'm Alex McColgan and you're watching Astrum. Join me today as we unravel Polaris's hidden companions, explore its peculiar behavior, and reveal why this star could reshape our map of the universe. No, really, wait and see. It's a moonless summer night, and you've wandered to your favorite stargazing spot. Looking up, you recognize Ursa Major, which contains the Big Dipper, a constellation of 7 stars in the shape of a ladle. You follow the 2 pointer stars up and up until you hit a noticeably bright star in the sky. This is Polaris. It sits almost exactly above Earth's rotational axis, so while all other stars appear to wheel around the sky, this one stays put. At the North Pole, Polaris appears nearly directly overhead. As you move south, it appears lower and lower in the sky until you reach the southern hemisphere and it disappears behind the horizon. But while we've relied on Polaris to navigate the world, it turns out that Polaris itself is far more mysterious and far more complicated than anyone once believed. To us down on Earth, Polaris appears as a solitary, unchanging point of light. That is, unless you use a telescope. In 1779, William Herschel did, and he discovered Polaris had a second star, Polaris B, in a wide orbit. 120 years later, in 1899, astronomer William Wallace Campbell noticed Polaris A had variable radial velocity, suggesting it might have another companion star, one not visible through a telescope. In 1929, a spectroscopic study confirmed this, and we only got our first images of the third Polaris star, Polaris AB, in 2006, thanks to the Hubble telescope. These 3 stars are bound together by gravity in a triple star system. The brightest component, Polaris AA, is what we think of as the North Star. It is an evolved yellow supergiant, 5.13 times the mass of our Sun and 46 times wider. If you placed it in our solar system, it would reach over halfway to Mercury. 2.8 billion kilometers away is its close companion, Polaris AB. Together, these 2 stars form a binary system that completes an orbit every 29.6 years. The third star, Polaris B, circles this inner duo every 40,000 years at a distance of 386 billion kilometers. That's about 24 times further than Voyager 1 is from us after 48 years of travel. Both Polaris B and A are yellow-white dwarf stars, about 500 times fainter than their primary star. Polaris B is 1.39 times the mass of our Sun, while Polaris AB is slightly smaller at 1.26 solar masses. But Polaris's triple star system is the least interesting thing about it. Its primary star, Polaris AA, belongs to a rare class of stars known as Cepheid variables, which, as it turns out, are one of the keys to mapping the cosmos. In 1908, an astronomer named Henrietta Leavitt was working at Harvard College Observatory, studying the Small Magellanic Cloud. She was looking at Cepheid variable stars, stars in a specific phase of stellar evolution which pulsate regularly, growing brighter and dimmer in predictable cycles. She discovered that there was a direct relationship between how bright a Cepheid appears and how long its pulsation period lasts. The brighter the star, the longer it takes to complete one cycle of pulsation. This turned Cepheids into standard candles, objects whose true brightness we can determine just by measuring their pulsation period. Since we know how bright they actually are, we can calculate how far away they must be based on how bright they appear to us. It's like knowing the true wattage of a light bulb. The dimmer it looks, the further away it must be. Cepheids became a crucial rung in what astronomers call the cosmic distance ladder, our method for measuring distances throughout the universe. Before the period luminosity relationship breakthrough, we could only measure objects a few hundred light years away using stellar parallax, a measurement of how far a star shifts in the sky as visible from Earth. But with this new discovery, suddenly scientists could measure intergalactic distances of millions of light years. Now we could use nearby methods like parallax to calibrate Cepheids, then use Cepheids to measure distances to other galaxies, which in turn helps us calibrate even more distant markers like Type 1a supernovae. As the closest Cepheid to Earth, you'd think that would make Polaris a goldmine for astronomical research. It could help us calibrate the size, age, and fate of the universe, everything from the distance to Andromeda to the rate of the universe's expansion. But here's where things get complicated. Turns out, Polaris AA is quite a weird Cepheid for a number of reasons. First off, its amplitude is erratic. Scientists noticed the difference between its brightest and dimmest points declined through the 1960s to 1990s, down from above 0.1 to below 0.05 magnitude. It leveled off and remained stable for a while before starting to creep up again in the year 2000, a pattern never seen in any other Cepheid. But it's not just its amplitude that's raised eyebrows. For the 150 years we've been observing it, Polaris's period of around 4 days has been increasing by 4.5 seconds per year. That's an incredibly fast rate of period change for a Cepheid, which suggests Polaris is evolving quickly. One theory astronomers have for this unusual behavior is that Polaris AA might be entering an unstable phase of its life. All stars go through an unstable phase when they leave the main sequence, but they don't necessarily all become Cepheids. What kind of pulsating star they become depends on several characteristics, including its mass, luminosity, and pulsation period, among other things. Most Cepheids go through 3 big instability events in their lives. The first happens very fast, lasting from 10 to 100,000 years. It occurs when hydrogen fusion in the center has stopped and the star leaves the main sequence, moving towards becoming a red giant or supergiant. It's the least studied of the instability phases because it's so brief, relatively speaking. The second instability occurs when the star begins burning helium in its core, stabilizing the star and making it burn hotter and bluer in color. This transition can take anywhere from 100,000 to 10 million years. When the star finally runs out of helium, it expands again and becomes unstable for the 3rd time, with a similar timeline as the second phase. Nearly all the Cepheids we've seen in these unstable phases have been in the 2nd or 3rd phase, making their behavior relatively predictable. But catching a Cepheid on their first instability is extremely rare, and their behavior in this state is much less understood. There isn't a consensus on which instability stage Polaris is in. Some claim it's in the 1st, while others say it must be in the 3rd. And just as these theories emerged to explain the changing period, Polaris suddenly reversed the trend. Since 2010, its period has been getting shorter year after year, and no one knows why. We think it might be due to Polaris AB disturbing it whenever they pass each other at their closest point, but no one knows for sure. But even more fundamental than that, there's still a key piece of the puzzle missing to fully understanding Polaris's properties, something embarrassingly simple that's proven brutally challenging to solve. You might expect that with modern technology, measuring the distance to our North Star would be straightforward, but it's actually trickier than you might imagine for a few reasons. Firstly, Polaris is hundreds of light years away. The further a star is, the smaller its parallax shift is. For context, the Hipparchus mission from the 90s measured Polaris's parallax as 0.00754 arcseconds, or 2.094 times 10 to the minus 6 degrees, an unimaginably small movement. On top of that, Polaris is so bright it can saturate our detectors, making our readings unreliable. Couple that with the fact it is a pulsating Cepheid star with a close companion, and brightness-based distance readings get even more complicated. All this makes Polaris's distance from Earth surprisingly hard to pin down. Estimates range from 323 to 520 light years away, and there's still no universal agreement in the scientific community. For example, Hipparchus mission placed Polaris at 434 light years, while the more recent Gaia data from ESA puts it at 447 light years away. Without a clear idea of how far Polaris is, estimating other properties like mass, radius, and luminosity is complicated. The mass and radius estimates I shared earlier are based on the Gaia data, but if we were to use different inputs, we'd get pretty different predictions. To make matters worse, the estimates we do have of Polaris's age, mass, and pulsation period don't seem to match our stellar evolution models whatsoever. And again, we don't really know why. For example, Polaris AA appears to be much less massive than we expected, and much younger than its companion Polaris B. We'll come back to this age discrepancy in a moment. One possible explanation is the limitations of the stellar evolution models themselves. Firstly, all stars rotate. This rotation can have profound effects on star structure, evolution, and pulsation behavior. However, modeling rotation is incredibly complex and involves many unknowns, so many researchers don't include this crucial factor in their stellar evolution models. For a star like Polaris AA, this omission could be leading to significant errors in our evolutionary predictions. Another possibility is that Polaris AA has lost mass during its evolution, perhaps through solar winds or interactions with its companions. Mass loss would explain the star's rapid period change and could account for some of the discrepancies with evolutionary models. Researchers have tried to estimate mass loss, with some studies placing it at 2 septillion kilograms per year. That's a 2 with 24 zeros behind it. But so far there hasn't been much convincing evidence to support this theory. And finally, 2024 observations using the Chara array detected giant star spots on Polaris AA's surface. These spots are consistent with the presence of a magnetic field, which might also affect the star's pulsations. If we're missing crucial physics in our understanding of how these stars evolve and behave, it could affect the accuracy of Cepheids as standard candles. And if our model of Cepheids is wrong, so is our map of the universe. Alright, Polaris is mysteriously pulsing faster and faster. We're not sure how far away it is, and it's making us rethink our stellar evolution models. As if that wasn't enough, Polaris has another ace up its sleeve. Remember that age discrepancy? If Polaris AA and Polaris B are gravitationally bound, as they seem to be, they most likely form together. This means we'd expect them to be the same age. However, our observations indicate the opposite. Assuming a distance of 447 light years, Polaris AA appears to be about 50 million years old, but estimates put Polaris B at 2 billion years old. So what happened here? A couple of theories have attempted to untangle this knot. One is simply that Polaris B is not a companion of Polaris A after all, despite strong evidence to the contrary. But another, more enticing idea hinges on a phenomenon we've known about since the 1950s. Globular clusters are dense environments of stars that all formed around the same time. And yet, in 1953, Alan Sandage noticed some stars appeared much younger than others. Bluer, hotter, and more massive, he named them blue stragglers. We think they form as the result of star collisions when binary stars merge. The result is a star that appears much younger than its true age. It's possible that this is what happened to Polaris AA. It could have been rejuvenated by a collision with another star, originally in close proximity to it. While this merger hypothesis is speculative, it demonstrates how the Polaris system challenges our understanding of stellar evolution and binary star formation. At the end of the day, this age gap remains one of the big enigmas surrounding the Polaris system. While the Polaris star is our North Star today, it won't stay that way forever. Earth's rotational axis wobbles, much like a spinning top. As a result, our celestial pole wanders in a close circle, sweeping past different stars. About 14,000 years ago, the celestial pole pointed towards the bright star Vega, and it will once again return to that position in about 12,000 years. For millennia, Polaris has guided humanity across oceans and deserts, but today it guides us in a different way, forcing us to confront what we still don't know about the stars, the universe, and even our own scientific limits. And as the next round of Gaia data approaches, set to release in mid-2026, we may finally get some more conclusive insight into this perplexing star system.
To us mere humans, Earth is vast. It takes days to travel from one side to the other. But leave the surface and it quickly becomes clear that we live on a tiny speck in a colossal universe, filled with innumerable planets and countless stars residing within trillions of galaxies. The universe operates on a scale that we simply cannot comprehend, let alone exhaustively explore. But within this grand structure lie individual beasts that, on their own, defy our understanding of scale. Stars so large, they make our sun pale into insignificance. And in the depths of the southern constellation Scutum, we think that we found the largest one yet. But just how big can a star get? And are there even bigger beasts waiting to be found? I'm Alex McColgan and you're watching Astrum. Join me as we climb the cosmic beanstalk into the kingdom of the universe's giants. You might think our sun is pretty big, and it is. With a radius of 700,000 kilometers across, if the sun were a football, or a soccer ball for you Americans out there, the Earth would be 109 times smaller, the size of a 2mm wide peppercorn. Even if you added up all the mass of all the solar system's planets, the sun would still be 743 times more massive than all of them combined. But when it comes to other stars, our sun is nothing special. Some of our closest neighbors, the Alpha Centauri binary stars, are a similar size, and Sirius A is twice as big. But how big can a star actually grow? To understand that, we need to look at stellar evolution. So our journey begins here, in the heart of something known as the Hertzsprung-Russell diagram. Independently invented in the early 1910s by both Danish astronomer Einar Hertzsprung and American Henry Norris Russell, it plots stars' temperatures against how bright or luminous they are. And running down the center of this diagram lie what's called main sequence stars. This spine is where most stars spend the majority of their lives. If they're here, it means they're in a stable phase of existence. Having gone through the chaotic molecular cloud collapse of birth, a main sequence star is now continuously fusing hydrogen in its core, generating energy that pushes outward against the brutal inward force of its own gravity. It's a balancing act, and once it's reached, a star is said to be in hydrostatic equilibrium. Almost all of the stars on the main sequence are in this state of so-called rest, but that doesn't mean they are all the same. Our Sun sits comfortably in the middle of the Hertzsprung-Russell diagram. It's a fairly average G-type main sequence star. The G is what's called the spectral class, which essentially classifies stars by their temperature and therefore color into a seemingly arbitrary naming system of OBAFGKM, where O is the hottest and M is the coldest. I remember it using the mnemonic, "Oh, be a fine girl, kiss me." Do with that what you will. The Sun and other G-type stars have surface temperatures around 5,778 Kelvin, giving them the yellow-white hue that we're all familiar with. Their cores steadily fuse hydrogen into helium, converting about 600 million tons of hydrogen per second and emitting energy that, in the case of our Sun, has powered life on Earth for billions of years. But if you move up or down the main sequence, the stars change and a pattern begins to emerge. It's probably not surprising that dim stars are usually cool, and that the hotter a star gets, the brighter it gets too, at least on the main sequence. But what might be less intuitive is how a star's mass relates to this. And there is a clear correlation. The brightest star also tends to be the most massive ones. Take, for example, Bellatrix, the 26th brightest star in the sky and the left shoulder of the Orion constellation. It's a B-type star, one of the brightest classifications, and has a surface temperature around 22,000 Kelvin, almost 4 times hotter than our Sun. It's also 8.6 times more massive. The effect of this greater mass is to crush the hydrogen in Bellatrix's core far more than in other stars. Greater pressure increases the rate of fusion reactions, and therefore, far more energy is released. This fusion is so powerful that it forces the star to swell. It's as if gravity almost can't contain it. So Bellatrix's volume is a whopping 200 times greater than our Sun's. But this comes at a price. Massive main sequence stars burn hot and fast. While the Sun will likely have a total lifespan of 10 billion years, Bellatrix has been burning for 25 million, and there's only 7 million years left. This actually makes large stars quite rare. Their instability and rapid existences mean we're simply less likely to see them than their longer-lived, less massive cousins. So, is that the answer then? If we want to find the largest star, should we simply seek out the heaviest? It's thought that stars can't grow much bigger than 150 times the mass of the Sun without becoming so unstable that they blow themselves apart. However, the universe has found ways to cheat when it comes to this limitation. When two massive stars collide and merge, the resulting star is a true behemoth, much larger than anything possible through the slow devouring of an accretion disk. Perhaps this is the explanation for the truly staggering and excitingly named R136A1, potentially the most massive and most luminous star in the universe. at the furthest top left point on our Hertzsprung-Russell diagram, R136A1 is a monster. Forget the 150 times mass limit. This beast has been estimated to be 265 times the mass of our Sun, and has a radius 40 times larger. It's part of a particularly rare group known as Wolf-Rayet stars. We found just 220 in our galaxy, although scientists expect there could be as many as 2,000. They are massive, and in an advanced but short phase of life, one that comes just before they collapse into supernova explosions. Because they are so unstable, they throw off vast amounts of plasma in great winds, ejecting as much as 10 solar masses every million years at speeds of up to 3,000 kilometers per second. But they are also incredibly luminous, with R136A1 releasing as much light in just 4 seconds as the Sun produces in a year. Although, to our eyes, it's actually only 164,000 times brighter than our star, because most of its radiation is UV light. To be honest, we're lucky to have seen this star at all. It will likely only exist for 3 million years, the blink of a cosmic eye. But this still isn't the universe's largest star, not by radius at least, because although it is certainly one of the most massive, there are far less massive stars that grow much larger. How? It turns out, the very largest stars have a trick up their sleeves, or rather, in their shells. So far we have focused on main sequence stars, those burning hydrogen in their core. However, as a star dies, eventually that hydrogen will run out, and without the explosive energy of fusion to keep it stable, a star's intense gravity causes its core to start collapsing. With this comes even greater pressure, which once again turns up the heat in the core. Eventually the core becomes hot enough to kickstart helium fusion, causing the star to enter an entirely new phase of life. But this heat is also enough to warm the outer shells of a star. They can reach temperatures that used to only exist at the center, and suddenly, hydrogen atoms in the outer layers are also able to start fusing. This causes the star to expand dramatically as it becomes a red giant. Our Sun's radius is currently 700,000 kilometers, but when this process begins, the Sun will expand to a diameter of 300 million kilometers, which will make it big enough to consume Mercury, Venus, and possibly even the Earth. This process can take place in stars 0.8 to 8 times the mass of the Sun. A current example of a red giant is the fascinating Mira A, which is part of the Cetus constellation. It's only between 1 and 1.2 times as massive as our star, and yet its radius is at least 332 times bigger. And this is just the baseline. Mira A pulses over the course of various 80 to 1000 day cycles. When those cycles align, Mira physically puffs up, so its maximum radius is actually much larger. It can reach around 402 times that of our Sun. But even a red giant isn't the biggest type of star. When you get to 8 solar masses, another classification appears, one that's even bigger. The red supergiant. Towering, mighty, vastly larger than their smaller cousins, but also doomed to a tragic end. These monsters of the universe will end their lives in an explosive supernova. But we're interested in the moments before that, when they swell to become the largest stars we see in the universe. Betelgeuse is one of them, with a diameter of 1.2 billion kilometers, making it more than 700 times the size of the Sun. If it was at the center of our solar system, all the rocky inner planets would be engulfed. Even Jupiter wouldn't escape. Now, These supergiants are violent beasts. In the last throes of their life, they pulse and throw out huge amounts of material, which makes it difficult to determine where the edge of the star ends and space begins. But despite its enormous size, we know even Betelgeuse isn't the largest star out there. There is one other candidate, and as I hinted at the beginning of this video, it lurks in the constellation Scutum. This is UY Scuti, and it is colossal. So vast that 5 billion suns could fit within it. Surprisingly, it's not very hot. In fact, it's 40% cooler than the sun and glows a somber red. Another red supergiant. Because of its vast distance and low temperature, UY Scuti is not actually visible to the naked eye. You need powerful binoculars or a small telescope to spot it. At a distance of 5 to 10,000 light years, there is some uncertainty about UY Scuti's true size, with many other candidates vying for the title of largest known star. But UY Scuti won't be around for much longer. It's already 10 to 20 million years old and may now only have a few million years left on the clock. Within that time, it may even get smaller, transforming into a yellow hypergiant. This class of star is incredibly bright, but in order to achieve this, it would first have to shed its outer layers, becoming even hotter to sustain the last possible fusion reactions. Hypergiants are capable of blowing off the mass of Jupiter in just one explosive burp, and they have lots of them. Filled with heavy elements like oxygen, carbon and nitrogen, these ejected materials can form vast clouds 10,000 astronomical units in length. That's 300 times the distance from the Sun to Neptune. And they are vital to the universe's development. These swirling expulsions mix with dust clouds and material from other stars, combining to create stellar nurseries filled with the ingredients for life. This is still several 100,000, if not a few million years away for UY Scuti. But there is a giant star that's even closer to this final destruction. We've only ever properly imaged one star outside the Milky Way, and it was WOH G64, a red supergiant, a bit like UY Scuti, 160,000 light years away in the Large Magellanic Cloud. Recent studies suggest it may have already turned into a yellow hypergiant. In the last 10 years, it has become dimmer as it's thrown off material and become shrouded in dust. The problem is, once you get to these distances, it's hard to measure things precisely. Maybe WOH G64 is actually bigger than UY Scuti. We don't know if stars can get bigger than this. It's unlikely, as giants like UY Scuti are scraping the edge of what's called the Hayashi limit. This is the maximum size a star can reach given its mass, and you can see it as a line on the Hertzsprung-Russell diagram. If a star crosses this line, then convection inside takes over and gravity starts to win, making it smaller. So one day we might find a star slightly bigger than UY Scuti, but it won't be by much, unless we're missing something. Perhaps there's a type of giant star we simply don't have in our galaxy. We don't know, and unfortunately we don't have the technology to find out. Yet. What I do know is that humans can't really wrap our heads around anything bigger than a few thousand kilometers, so the scale of the biggest stars is far beyond our comprehension. They are cosmic monsters. But in the grand scheme of things, even these stars are tiny. Galaxies are tens of thousands of light years across, millions of light years apart, and individual filaments of cosmic web stretch billions of light years through space. The universe is so vast, we can't even begin to pretend to understand it all. That doesn't mean we can't try though. And bigger isn't always better. I think living on a tiny planet around an average star is working out pretty well for us so far. Betelgeuse is a super interesting star. Not only does it have an incredible name, but it's one of the closest red supergiants to us, meaning that while it is cooler than the majority of star types, it has an enormous diameter. If it was the star in our solar system, everything up until the asteroid belt would be contained within it. It's about 700 light years away from us, a lot further away than most other visible stars, but because it is so large, it's the 10th brightest star to the naked eye in the sky, and brightest in the infrared. It's easily visible as the left shoulder of Orion. If you do look for it in the night sky, it is also visibly redder than any of the surrounding stars, and it does a lot of twinkling. There's something else very special about Betelgeuse. It is likely to explode in a supernova at any moment. Although I say that in astronomical timescales. That means it could still take 100,000 years. How do we know that? Well, you see, large mass main sequence stars, or stars in the adulthood phase of their existence, are powered by the nuclear fusion that goes on within their core, converting hydrogen to helium. This fusion creates an internal pressure, which combats the effect of gravity wanting to compress the star into a smaller volume. However, eventually, the hydrogen fuel in the core will run out, having been converted to helium, meaning the fusion process stops, and the star's core can't overcome the effects of gravity anymore. The core compresses, but if the star is massive enough, the compression will trigger fusion again, this time with the helium in the core into heavier elements like carbon, with this process repeating for oxygen and neon. With every new fusion cycle, the star's internal pressure expands the diameter of the star until it begins the red supergiant phase of its life, when the core is being converted predominantly into iron. Red supergiants can't fuse anything beyond iron, so once the fusion stops, the star collapses completely into a supernova. And that's where we are at with Betelgeuse now. We are awaiting this final collapse. Whenever it does explode, it will eject its atmosphere far into space, which will be visible in our sky for a good 2 to 3 months before it dims again. It is far enough away that no harm will befall us on Earth, but it will make quite the spectacle, perhaps being as bright as a full moon, so even visible during the day. Now, something else very interesting has been going on with Betelgeuse. It's been in the news a lot, like in 2009 when it contracted in size by 15%. You may have also heard this year that Betelgeuse has been dimming, and scientists didn't really know why. Speculations were running rampant that this could be a precursor to this promised supernova. Although, perhaps sadly, this is likely not the case. New data from the Hubble Space Telescope has shown that the star itself may not really be dimming, but rather that some dust which was ejected by the star may have cooled and obscured the view. In September 2019, Hubble saw heated material moving away from the star's atmosphere. Over the course of the next few months, this material was observed near the star. By December, the star began dimming in its southern hemisphere. It is theorized that heated carbon was in the outflow, and as it moved around the star, it expanded, which cooled it down. When we lost sight of it, it didn't move away from the star, but rather crossed over our view of Betelgeuse. At its peak, Betelgeuse was 2/3 dimmer than normal. However, since April 2020, Betelgeuse has actually returned to its normal brightness. So this cloud has either moved out of the way or totally dispersed. So maybe this wasn't the exciting conclusion to this story you were looking for. Probably no supernovas for a while yet. But maybe that's a good thing, because after the event, Betelgeuse will no longer be visible. So next time you have a clear night, find Orion in the sky and have a new appreciation for the red twinkly star of Betelgeuse. When we look out into the vast, expansive, awe-inspiring cosmos, there are innumerable stars out there. Yet,
one of them dominates our sky and our lives, burning brightly and ferociously at the center of our solar system, the Sun. It's easy to see how generations of humans before us were inspired to create all kinds of legends to explain its mesmerizing glow. Now, as technology has advanced beyond the realms of their wildest imaginations, we can delve into the processes within and around our neighboring yellow dwarf, going deeper than ever before. As we journey through its ferocious atmosphere, let's explore what I'm sure you'll agree are the fascinating phenomena that materialize there. I'm Alex McColgan and you're watching Astrum, and in this video I want to dive into the Sun, drawing on different wavelengths of electromagnetic energy to showcase the star in a new light. Previously, we've explored Jupiter and some of its moons through the lens of the electromagnetic spectrum, which you can see in this video here. Today, we will be revisiting this approach, but this time, rather than a planet, it'll be adapted to investigate a highly energetic ball of plasma. The light we'll be looking at is old. Although light is the fastest thing we know, the image of the Sun that we see from Earth is approximately 8 minutes and 20 seconds old, meaning we are viewing what the Sun looked like a few minutes in the past. And if you count how long it takes the photons generated within the Sun's core to make their way through each layer of the Sun before escaping into space, the light that reaches us is anywhere from 10,000 to 170,000 years old. Where to begin? Like eating a fruit by starting with the outer layers and working your way in, let's start our investigation with the outermost layer of the Sun's atmosphere, the corona. The following image was taken by the Solar Dynamics Observatory, or SDO, a NASA space mission launched back in February 2010. SDO aimed to better understand the solar variations that influence life on Earth and our technological systems by studying the dynamic solar surface and atmosphere at different electromagnetic wavelengths. By looking at light beyond the visible range, NASA was able to pick out normally invisible details crucial to our understanding of the Sun. This image was taken using a 19.3 nanometer wavelength, representing light found in the extreme ultraviolet region. At a wavelength corresponding to a color temperature of 1 million Kelvin, we can clearly see the higher region of the Sun's corona. Interestingly, the Sun's corona can also be seen by the naked eye on rare occasions, such as during a total solar eclipse. When the Moon is perfectly aligned between the Earth and the Sun for a fleeting period of time, the view of the central, brighter disk, known as the photosphere, is fully blocked, revealing a radiant exterior. While this is a breathtaking view already, the corona is still nowhere near as detailed as it is in this image taken by the SDO. This makes it a useful tool for scientists' studies. But let's go a little deeper, to features of the Sun just beneath the corona. At a color temperature of 20 million Kelvin, the intensely vivid spots indicate events known as solar flares. Here is some footage of a particularly busy week for flares back in August 2022. I've always found solar flares to be both terrifying and hypnotizing. They are colossal explosions where the Sun spews out an immense amount of electromagnetic radiation. They are caused when magnetic fields cross, distort, and reorganize themselves rapidly. This activity is created by the turbulent nature of the plasma within the Sun itself, from which the fields ultimately originate. But they are not the only feature of the Sun's atmosphere venting radiation. Coronal holes, indicated here by this darker region on the Sun, are another fascinating feature which we'll take a closer look at using extreme ultraviolet light. Coronal holes are areas of cooler, less dense plasma which are magnetically open, meaning that rather than forming closed loops that go back to the Sun's surface, the field lines travel outward across the solar system. These areas allow solar wind particles to escape more easily into space. When these solar winds are directed towards and collide with Earth's magnetosphere, beautiful auroral lights dance across the night sky at the Earth's polar regions. Using ultraviolet light gives us a much better view of these fascinating features of the sun's outer layers. Non-visible spectrum light is an incredible tool, and there are so many different features in the sun's outer layers to look at. There are solar filaments, known as solar prominences, the large loops of plasma that rise from the sun's surface. These enormous loops are large enough to make the Earth look like a tiny speck and can stretch hundreds of thousands of kilometers into space. They can form in as little time as a day, but a stable prominence can remain in the corona for several months. In this example, we watch as a solar prominence snakes its way out of the photosphere and into the sun's atmosphere. Although this video is sped up so the minutes seem like seconds, when you consider the size of the prominence, it becomes clear how swiftly the sun's intense magnetic fields are causing this material to move. One fact you might not know about the sun's atmosphere is that it sometimes rains there. Not all of the charged plasma fired into the sun's corona continues out across the solar system. Some remains in the corona, getting trapped and cooled until it falls back to the sun's surface as a shining rain. This coronal rain is beautiful to look at, but is best observed from a distance. It's still millions of degrees in temperature. Of course, falling gently back to the sun's surface is only the fate of some of the sun's plasma. This is where the comparison to Earth fails. After all, on Earth, the clouds do not crack like a released elastic band firing into space. On the sun, thanks to tightly wound magnetic fields, they do. This is a time-lapse of a coronal mass ejection. Watch as the structure forms at the bottom left of the sun for some time, before eventually snapping and sending billions of tons of plasma out across the solar system. Even with the Earth's magnetic field, being hit by a powerful one of these could be devastating for our satellites and electrical grids. All these structures are imaged by the SDO here utilizing a 30 nanometer wavelength of light, which corresponds to the extreme ultraviolet portion of the electromagnetic spectrum. Timing is important when trying to image these features, as they are more common in certain years than in others. In fact, each structure is dependent on the solar activity of the sun, alternating around an 11-year solar cycle, which I did a video about here. But there's more to learn. Just as using visible and ultraviolet light shows us different things when looking at the same feature, using two different wavelengths of non-visible light can also be eye-opening. To demonstrate this, take a look at these two images of the sun's corona. Taken over the same time period, the following two images use different wavelengths of light. The first, imaged at a color temperature of 600,000 Kelvin, depicts the quiet corona and features coronal loops. The second, imaged at a color temperature of 2 million Kelvin, displays the much hotter active regions of the corona. The stark comparison between the two images highlights the importance of using different approaches when investigating the star. What may initially appear to be a singular solar phenomenon can be revealed as a complex, intertwined chain of events, and we still haven't technically made it through the sun's atmosphere yet. Moving further inwards, let's look at another image produced by the SDO utilizing a 160 nanometer wavelength of light, this time of the transition region. The transition region is a layer which sits between the sun's corona and the chromosphere, the lowest layer of the sun's atmosphere. It's a very shallow layer, approximately 100 kilometers in thickness. In this region, the thermal temperature of the sun rises dramatically from around 8,000 to 500,000 Kelvin. For an earthly comparison, fiercely scalding lava erupting in Hawaii is 1,170 degrees Celsius or 1,443 Kelvin. The temperature at the lower, deeper end of the transition region is almost 6 times hotter than this. At the upper end of the transition region, the temperature is more than 346 times hotter. Traveling even deeper, we find ourselves immersed in the Sun's chromosphere, which is the last layer of atmosphere before we reach the Sun's surface itself. Imaged here, using 170 nanometer ultraviolet light, it is estimated to be approximately 1,700 kilometers thick. Closely inspecting the chromosphere, we identify some mesmerizing features known as spicules. Swaying like long, wavy grass blowing in the wind, these long jets of plasma shoot upwards from the Sun's surface at speeds up to 100 kilometers per second, approximately 282 times faster than the speed of sound, and can reach lengths of nearly 10 kilometers, over 1 kilometer taller than Mount Everest. Forming and vanishing in around 5 to 10 minutes on average, the processes behind these spicules were widely unknown and debated for some time, as it wasn't clear how magnetically charged particles could ever escape the Sun's magnetic fields at that level. That is, until 2017, when a team of scientists working on an extremely detailed model of the spicules discovered that their origins must be related to neutral particles. Scientists had not originally included neutral particles in their models of the Sun, as they didn't think they affected the motion of the magnetically charged particles. But once they were added, it transpired that the neutral particles gave the magnetically charged particles unexpected buoyancy they needed to escape the Sun's plasma and shoot up into spicules. Descending further through the Sun's lower atmosphere, we eventually reach the photosphere, the surface of the Sun itself, which is best imaged using visible light. While the edge of the photosphere appears sharp and precise, as it often does to our naked eye, this is simply due to how far away the Sun is. The Sun itself is not solid at all. Since it is too hot for matter to exist in a solid, liquid, or gas state in any region of the Sun, it can only be plasma, referred to as the fourth state of matter, and is estimated to make up 99.9% of all the matter in the universe. Plasmas tend to behave a lot like gases, except they are made up of a mixture of ionized atoms and free electrons. The photosphere is the outermost layer in this image, around 400 kilometers thick. It is not a fixed, solid boundary of the Sun, unlike what this image may suggest. And sadly, it is the deepest layer of the star which scientists can measure directly. At a closer look, you may notice some dark spots on the left-hand side. These are known as sunspots and appear darker than other parts of the photosphere due to their cooler temperatures. But that's only in comparison to their scorching hot surroundings. Unlike coronal holes, sunspots form in areas where magnetic fields are particularly powerful. Here, heat becomes trapped beneath the photosphere due to decreased convection within these areas. When comparing this image of the Sun to a previous one taken using extreme ultraviolet light over the same period, a connection between sunspots and solar flares emerges. The captivating solar flares and sunspots coincide at the same location. From peering beneath the surface, it becomes clear that one must lead to the other. Now, let's take a closer look at some similar sunspots. This image was taken using the Swedish Solar Telescope, based here on Earth, and using a wavelength of visible light of approximately 400 nanometers. Next to and surrounding the sunspots, the photosphere is saturated with these jagged-edged, endlessly shape-shifting cells, which doesn't look dissimilar to lava as it cools and cracks. However, these cells are around 1,000 kilometers wide and are known as solar granules. Consider them from the top layer of a churning convection cell underneath. Brighter areas inside each granule represent fluid of unimaginable temperatures rising from within the Sun's upper interior layer to its surface. Upon reaching this boundary, the fluid has nowhere to go except to spread outwards and across. After cooling gradually, the fluid sinks back inwards via the rough, dark boundaries surrounding each cell, before repeating the cycle. This process closely resembles the convection currents within the Earth's mantle, responsible for driving plate tectonics. This process is no joke. While on average it is estimated that each granule lasts for as little as 20 minutes, the flow within the cells reaches supersonic speeds of more than 7 kilometers per second, generating waves on the sun's surface due to sonic booms. Fascinatingly, these granules can also be seen in the full disk view we saw earlier, utilizing the same wavelength of visible light. You may think this image looks quite grainy for such a high-tech space probe, and you're right, it does. But that graininess is the granules on the photosphere of the sun, not a processing effect or excess noise in the image. And that's it. Sadly, our journey ends here, as scientists have not yet figured out how to image deeper into the sun, using either visible or non-visible light. Much of what lies beyond this layer remains shrouded in mystery, but we can see the benefits of using light of all different spectrums in our study of the sun. They help us observe exploding solar flares, vast coronal holes, swaying spicules, intriguing sunspots, and shape-shifting cells, just to name a few, in completely new ways. The sun is abuzz with lively activity, and so much of it would be invisible to us were it not for these imaging techniques. Maybe one day we'll find ways to see deeper, using techniques we can barely dream of currently, just like those ancient generations of humans long ago could hardly dream of the methods we're utilizing these days. But for now, just knowing there is so much going on unseen in the universe, and knowing we have the means to uncover it, fills me with excitement and curiosity. Who knows what else might be out there, waiting to be found.
You may have wondered, with the vast distances between objects in space, and with the lack of a tape measure that big, how can scientists be sure they know the distances between us and other celestial bodies? Well, there are a few methods available depending on how far away the object is, each with a varying degree of accuracy. The first method is the most accurate, and in fact gives us very precise measurements. This is the parallax method. For those of you that don't know what the parallax effect is, it is where nearby objects appear to move more compared to objects far away as you travel parallel to them. For instance, when you look out of a side window in a car, everything close by whizzes by, but objects in the background stay reasonably still. How does this equate to measuring the distance between stars? Well, Earth orbits the Sun, taking 6 months to reach from one side to the other. Scientists can look at a star and record its position compared to distant stars beyond it. In 6 months' time, scientists can again record where the star is. Because we know the diameter of Earth's orbit is roughly 300 million kilometers, using simple trigonometry, we can work out the distance to the star. Is the star close to us? Then the differences in its apparent location will be much bigger. Is it further away? The star's position will only change very slightly because the angle is much smaller. This method works up until about a distance of 400 light years, as beyond that the change in its apparent motion can't be measured anymore. Earth's orbit would have to be a lot bigger before you could use this method for farther distances, which is unfortunate because most things in space are further than 400 light years away from us. But thankfully, there are very clever scientists out there that have come up with another method to judge distances without having to use trigonometry. Although it should be mentioned that this method is slightly less accurate. It's just simply the best we've got. It seems that stars tend to follow a pattern, which can be seen on this chart. Main sequence stars, which make up the majority of stars in the universe, can all be found somewhere along this band. Their temperature corresponds to their color, and most importantly, their brightness. Using stars that have a confirmed distance thanks to the parallax method, we can see how much a star dims due to the distance between it and us, and extrapolate that far beyond 400 light years. So, say we see a very blue star that we want to know the distance to. Once we know the star's precise color, we can tell how bright it would be if it were right next to us. We can then measure the star to see how bright it is from our perspective. Combining this with our extrapolated data, we can predict how far away the star really is. Obviously though, there is some margin of error in our predictions. This band is quite thick after all, not a precise thin line. So these two methods work for stars in our own galaxy, where they are still close enough to be resolved individually. But what about other galaxies? How do we measure the distances to them? Well, we would have struggled were it not for the universe being kind to us by gifting us Cepheid variables. A Cepheid variable is a very special type of star that changes in brightness periodically depending on how bright it is. And some of these stars are very bright indeed, so much so that the changes in brightness can be detected by us all the way in a different galaxy. Timing the pulses in a Cepheid variable, we can know exactly how bright the Cepheid variable should be and how dim it is to us, allowing us to use the extrapolated data again to work out the distance to it and to the galaxy it resides in. Beyond that, it gets much more complicated and less accurate. With galaxies billions of light years away, you have to start taking into account the expansion of the universe and redshift. And the distances make seeing the galaxies at all very difficult, as they require long exposure photos, which will blur the variations in light produced from Cepheid variables, assuming they are bright enough to be seen at all. However, the universe has given us one more measuring stick to work with, type 1a supernova. These are a very specific type of supernova, where in a binary star system, a dense white dwarf starts to cannibalize a larger red dwarf. Once the white dwarf hits a critical mass, the star becomes unstable and undergoes a runaway nuclear fusion reaction, producing an extremely bright event that can rival an entire galaxy in brightness. Because these supernovae always happen to a white dwarf that hits a very narrow range of mass, the rise and fall of their brightness is very predictable. And given they are very bright events, they have been used to measure distances of up to 13.2 billion light years. However, there aren't always these type of supernova going off, which means if scientists want to use this method, then they need to be very patient. There are a few other methods out there too, but this covers the main ones. To me, these are incredibly clever methods to measure distances, and credit to the scientists who came up with them in the first place. The only sad thing about realizing how far away everything is knowing how hard it will be to cover those distances should we ever want to explore beyond our own solar system.
A massive thank you to our astronauts on Patreon. This video had no sponsors, but it was still made possible thanks to the hundreds of members we have there. Link is in the description to join our growing community. Patreon is where Astrum truly takes shape, a place for people who love space, who want to see these videos keep improving and reaching more curious minds. Every new member keeps the channel focused on what really matters, making the complexity of space available to everyone. If you enjoy what we do, come join the Astrum community today.